Photoelectric effect, the topic for which Albert Einstein was awarded the Nobel Prize in Physics. The photoelectric effect is a phenomena in which electrons are ejected from the surface of a material when light is incident on it. Even though initially it was extensively studied on metals, it is a general phenomena as it takes place even in semiconductors. You will study devices based on this concept. One such example is light emitting diode. Photoelectric effect is a phenomena in which electrons are ejected from the surface of a material when light is incident on it. These ejected electrons are called photoelectrons. The emission of photoelectrons and the associated kinetic energy is dependent upon the frequency of the electromagnetic wave that is incident on the surface. The process through which photoelectrons are ejected from the surface of a material due to the action of electromagnetic wave is commonly referred to as photoemission. The photoelectric effect occurs because electrons at the surface of the material tend to absorb energy from the incident light and use it to overcome the attractive forces that bind them to the atomic nuclei. Photon energy is given by h nu, where h is the Planck's constant whose value is equal to 6.626 into 10 raised to the power minus 34 joule second, and mu is the frequency of the incident light in hertz. The Planck constant is a proportionality constant between the energy carried by a photon and the frequency of its associated electromagnetic wave. Now we will be discussing the photoelectric effect with respect to semiconductor. As you can see in the diagram that a photon hits an electron leading to its transition from valence band to conduction band. In the shown diagram, E1 and E2 are the energy levels of conduction band and valence band respectively. We just discussed energy E is equal to h nu, and also we know C is equal to mu into lambda, where C is speed, mu is frequency, and lambda is the wavelength of electromagnetic wave. It gives us mu to be equal to C upon lambda. Now, putting this value in the previous equation, we will get, if we assume delta E, E1 and E2 all are in electron volts, then E1 minus E2 is the difference in energy level which represent the minimum amount of energy required by a photon to knock out an electron from valence band to conduction band. Delta E means the difference in energy and hc upon lambda is the energy of the photon. We have just equated these two energies. We also know that C and H are constant. By putting the value of C and H in the equation, we will get wavelength in Armstrong 2V equal to 12400 divided by bandgap energy in electron volt. Through this formula, you can find wavelength in Armstrong if energy difference is provided in electron volt. While solving numerical problems, check carefully in which unit data is provided and also in which unit the answer is asked.